Hello and good day. Gentlemen, my name is Shahid Khan and I am a chemical engineer. I have prepared a training course on valves and their applications. This course will refresh your knowledge on valves. This course is beneficial for all personnel from operators to engineers who are working in industry, especially oil and gas. After completing this course, you will be able to explain the purpose of valves in industrial manufacturing. Identify the basic components of a gate valve. Identify the basic components of a globe valve. Explain the operation and design of a ball valve. Identify the basic components of a check valve. Describe the design and operation of a butterfly valve. Examine the design and operation of a plug valve. Describe the design and operation of a diaphragm valve. Describe the design and operation of a relief valve and a safety valve. Describe the design and operation of automatic valves. Before starting course, let us have a look at key terms. Accumulation is the pressure difference, delta P, between initial lift pressure and full lift pressure on a relief valve. Actuator is a device that controls the position of the flow control element on a control valve by automatically adjusting the position of the valve stem. Angle valve is a valve that operates by admitting fluid flow to the gate or plug and redirecting it 90 degrees out the discharge port. Anti-seize compound is a lubricant used on exposed valve stem threads. Ball valves are named for the ball-shaped, movable element in the center of the valve. Block valve is any valve that is intended to block flow, also called an isolation valve. The term generally refers to gate valves. Bonnet is a bell-shaped dome mounted on the body of a valve. Bridge wall markings is manufacturer information on the body of a valve. Butterfly valves are characterized by their disc-shaped flow control element, which pivots from its center. Check valves are mechanical valves that prevent reverse flow in piping. Control loop is a collection of instruments that work together to automatically control a process, usually consists of a sensing device, a transmitter, a controller, a transducer, and an automatic valve. Control valves is an automated valve used to regulate and throttle flow, typically provide the final control element of a control loop. Diaphragm valve is a device that uses a flexible membrane to regulate flow. Disc is a device made of metal or ceramic that fits snugly in the seat of a valve to control flow. Flange is a device used to connect, bolt, piping to industrial equipment. Flow control element is the part of a valve that regulates flow, that is, the gate or the disc. Fluid is of the three forms of matter: solids, liquids, and gases. Liquids and gases are considered fluids. Gate is the flow control element of a gate valve. Gate valve is a device that places a movable metal gate in the path of a process flow. Globe valve is a device that places a disc in the path of a process flow. Handwheel is attached to the valve stem and used to control the position of the flow control element of a valve. Multiport valve has multiple inlets and/or outlets in specialized piping systems to divert flow direction, allowing fluid sources to be switched. Needle valve is a type of globe valve that has a needle-shaped element that fits snugly into the seat. Packing is a specially designed material used to stop fluids from entering or escaping, packed around the shaft or stem of a valve or shaft of a pump. Packing gland is a mechanical device that contains and compresses packing. Plug valve is a device that has a plug-shaped element, used for on-off service. Safety or relief valve is a device set to automatically relieve pressure in a closed system at a predetermined set point. Relief valves are used for liquids. Safety valves are used for gases. Stem is a metal shaft attached to the handwheel and flow control element of a valve. Stuffing box is the section of a valve that contains packing. Three-way valve is a valve with 3 ports, 1 inlet and 2 outlets, used to divert flow direction. Throttling is reducing or regulating flow below the maximum output of a valve. Trim is the flow control element and seats in a valve. Valve capacity is the total amount of fluid a valve will pass with a given pressure difference when it is fully open. Warping is a term used to describe temperature changes in pipe expansion that cause a valve to seize or warp. Closing a valve too quickly can cause warping, and warping can cause a valve to stick. Valve applications and theory of operation. Process plants are a network of complex systems and processes. Just as arteries, veins, and the heart are vital to human life, pipes, valves, and pumps are indispensable in a process plant. The primary purpose of a valve is to direct and control the flow of fluids by starting, stopping, and throttling or restricting flow to make processing possible. Valves are designed to withstand pressure, temperature, and flow and can be found in homes and industry across the world. The common valves shown in picture or found in the manufacturing environment are gate valves, globe valves, ball valves, check valves, butterfly valves, plug valves, needle valves, three-way valves, diaphragm valves, relief and safety valves, angle valves, and multiport valves. Valves normally are selected for a specific purpose. As you continue through this course, you will notice the variety of valve designs that exist. Operators need to be aware of how each valve works and the specific service for which it was designed. Classification of valves. Process operators classify valves by 1. Flow control elements, 2. Function, and 3. Operating conditions such as pressure, flow, or temperature. The most common way to classify valves is by the valve's flow control element design. This part of the valve controls or regulates the flow of fluid through the device. Some valves have movable metal gates, balls, plugs, diaphragms, discs, needles, or even butterfly-shaped elements. Most valves are named for the type or design of the flow control element. Valves that are used for isolation are classified as block valves. While gate valves are the most common valve used for isolation, any valve can be used for this type of service. Another term associated with valve operation is valve capacity. Valve capacity is a term used to describe the total amount of fluid a valve will pass with a given pressure difference when it is fully open. Bridge wall markings. The body of the valve contains bridge wall markings, which provide manufacturer information specific to the valve. The bridge wall markings include the following letters and symbols. W indicates low temperature water service. O indicates low temperature oil service. G indicates low temperature gas service. Arrow indicates flow direction. Additional information on size and pressure rating is sometimes found on a plate attached to the handwheel. Gate valves. One of the more common valves found in industry is a gate valve. A gate valve places a movable metal gate in the path of a process flow in a pipeline. The gates are sized to fit the inside diameter of a pipe, so very little restriction occurs when it is in the open position. Valves vary in size from 0.125 inches to several feet. Gate valves typically are operated in the wide open or completely shut position. This type of valve is used where flow rates are not restricted. Gate valves should not be used to throttle flow for extended periods. Turbulent flow rates across the valve body will cause metal erosion, seat damage, and damage to the flow control element, which can prevent the valve from blocking the flow completely. The seats in a gate valve fall into two categories, replaceable and fixed. Smaller valves typically have fixed or cast seats because it is easier and more cost-efficient to replace the valve than to replace the seats. In most cases, a gate valve has two vertical seating surfaces. The edges of the seats match up with the parallel discs or wedge. The typical gate valve consists of a gate, body, seating area, stem, bonnet, packing, stuffing box, packing gland, and handwheel is shown in picture. The gate can be wedge-shaped or may consist of parallel discs. It can be composed of a variety of materials. The gate is placed directly in the path of a process flow when it is shut and is lifted completely out of the way when open. The body is the largest part of the valve. The body can be connected to the process piping in three ways: flanges, threaded connections, or welding. The rest of the valve is attached to the body. The seating area consists of two fixed surfaces or rings inside the body of the valve that the gate closes against to stop flow. The seating area falls into two categories, replaceable or fixed. Seats must provide a clean mating surface for the gate to seal properly. The seat can be fabricated or cast as part of the valve, press fit, threaded, or welded into place. Note that high temperature and high pressure situations may require a combination of threading and welding. The stem is a long, slender shaft attached to the gate, bushing, or wheel. When the hand wheel is turned, it transmits rotational energy to the stem, causing it to rise to open or lower to close. The bonnet provides a housing for the gate or disc when it is lifted out of the process flow. It is attached to the body permanently by welding or temporarily by threading or bolts. The packing is a specially designed material that prevents leakage from the bonnet, yet allows the stem to move up and down smoothly. The stuffing box is typically located where the stem goes through the bonnet. The stuffing box is a recessed area specially designed to allow packing to be mounted around the stem. The packing gland is a device used to compress and secure the packing material into the stuffing box. The packing gland nuts are designed to be evenly tightened by a technician to stop leaks. The hand wheel is attached to the valve stem. The hand wheel transfers rotational energy to the stem. This rotational energy controls the movement of the flow control element. Turning the hand wheel clockwise closes the valve. When the hand wheel is turned counterclockwise, it is opened. Common gates. The gate on a gate valve comes in a variety of shapes and sizes. The most common designs include the solid wedge, solid split gate, and parallel discs as shown in picture. The solid wedge gate forms a positive seal when the solid metal gate slips into the seat. A set of guides keeps the disc aligned. Because the solid wedge gate is designed to fit snugly into the seat, it should never be over-tightened. Excessive force will damage the seats, so the technician should shut the valve until it seats and then back off slightly. The solid split gate forms a positive seal when the split metal gate slips into the seat. The solid split gate is designed like the solid wedge but has a split element feature that makes it operate like a double disc. The split, non-jamming feature lets this type of gate handle higher temperatures than the solid wedge. Fluid pressure is used to seat this type of gate. The parallel, or double, discs gate is composed of two separate discs mounted to a shaft. Some parallel discs have a spring located between the two discs, whereas others are attached to a solid metal core. The double discs gate valve is designed for high temperature service because of its non-jamming design. As fluid enters this type of valve, it pushes against one of the discs, compressing the spring or flow control element and forcing the opposite disc snugly into its seat. System pressure helps position the gate in its seat. The higher the pressure, the more tightly the disc fits into the seat. Gate valve materials. Gate valves, as shown in picture, are designed to be used in a variety of process conditions. The specific condition dictates what type of material the valve will be made of. For example, stainless steel gate valves are used in corrosive, high and low temperature services. Specialty alloy gate valves are used in high temperature, high pressure service. Bronze gate valves are used in low temperature, low pressure service. Brass gate valves are used in low temperature, low pressure service. Cast iron gate valves are used in water, lubrication, and some low-pressure steam services. Gate valves are considered excellent devices for process services that are used intermittently. It is not uncommon to find gate valves that have not been operated for many years. Rising stem and non-rising stem. The stem on a gate valve comes in two designs, rising stem and non-rising stem. Located at the top of the gate valve is the hand wheel. The hand wheel is attached to a bushing, which is attached to the threaded stem. As the hand wheel is turned counterclockwise, the stem in the center of the hand wheel rises. As the stem rises, the gate is lifted out of the valve body, allowing fluid to flow. A process technician can look at this type of valve and tell if it is open or closed by checking the position of the stem. Another type of rising stem valve is threaded at the bottom of the stem. In this type of valve, the handwheel is firmly attached to the stem and rises with it as the valve is opened. A non-rising stem gate has a collar that keeps the stem from moving up or down. The handwheel is attached firmly to the stem of a non-rising gate. Turning the handwheel screws the stem into or out of the gate. You cannot look at this type of valve and tell if it is open or closed. Maintenance of rising stem and non-rising. Maintaining equipment is an important part of an operator's job. Valve stem threads exposed to weather need to be lubricated with anti-seize compound to keep them operating properly. The packing should be inspected and the gland nuts tightened evenly if a leak is found. Valve stems should not be painted, and every effort should be made to keep them free of dirt and dust. When closing a gate valve, the operator should take care not to damage the valve seats. Temperature changes, closing a valve too quickly, and pipe expansion can cause a valve to warp. Because warping can cause a valve to stick, the process technician should close valves slowly. When the gate is on the bottom, a wrench should never be used to snug it down. Many valves have grease fittings, which admit lubricant to moving parts. Process technicians routinely inspect, clean, and lubricate valves. Globe valves. Globe valves are the second most common valves used in industry. A globe valve places a movable metal disc in the path of a process flow. This type of valve is most commonly used for throttling service. The disc is designed to fit snugly into the seat and stop flow. Process fluid enters the globe valve and is directed through a 90 degrees turn to the bottom of the seat and disc. As the fluid passes by the disc, it is evenly dispersed. Globe valves must be installed properly to work efficiently. If the valve is installed backward, it will tend to wear unevenly and push the flow control element down. The typical globe valve consists of a disc, body, seating area, stem, bonnet, packing, stuffing box, packing gland, handwheel, and back seat as shown in picture. The disc is attached to the stem in three ways: slip joint, threading, or one-piece manufacturing. The disc can be classified as plug, ball, composition, or needle-shaped. It is composed of a variety of materials. The disc, or flow control element, rests in the seat, directly in the path of a process flow when it is shut. Unlike the gate valve, the globe valve is designed to be used for throttling. Flow can be regulated by the percentage of opening of the flow control element. The body is the largest part of the valve. The body can connect to the process piping in three ways: flanges, threaded connections, or welding. The rest of the valve is attached to the body. The seating area comes in four designs: cone-shaped, beveled flat surface, O-ring or washer, and tapered or needle-shaped cone. The seating area is where the flow control element closes against the body of the valve to stop flow. The seating area can be replaceable or fixed. Seats must provide a clean mating surface to the flow control element to seat properly. The seat can be fabricated or cast as part of the valve, press fit, threaded, or welded into place. High temperature and high pressure situations may require a threading and welding combination. The stem is a long, slender shaft attached to the disc, bushing, or wheel. Turning the handwheel transmits rotational energy to the stem. The bonnet provides a housing for the disc when it is lifted out of the process flow. It is attached to the body permanently by welding or temporarily by threading or bolts. Packing is a specially designed material that prevents leakage from the bonnet yet allows the stem to rotate evenly. The stuffing box is typically located where the stem goes through the bonnet. The stuffing box is a recessed area specially designed to allow packing to be mounted around the stem. The packing gland is a device used to compress and secure the packing material into the stuffing box. The packing gland nuts are designed to be evenly tightened by an operator to stop leaks. The handwheel is attached to the valve stem. The handwheel transfers rotational energy to the stem. This rotational energy controls the movement of the flow control element. The back seat is a device used to provide a seal between the stem and the bonnet and to protect the packing from excess pressure inside the valve. It is used in steam service. The back seat is manufactured as part of the stem. When the stem is in the full open position, the disc-shaped back seat firmly connects with the mating surface of the bonnet seat. For common disc designs, the disc on a globe valve comes in a variety of shapes and sizes. The four most common designs are plug, ball, composition, and needle as shown in picture. The plug-type disc is used for throttling. It is equipped with renewable seat rings on a cone-shaped mating surface. It is the best device for throttling and in situations with wide temperature and pressure variations. The ball element seats against a beveled, ball-shaped, or flat surface. It is designed for on-off applications that have minimal throttling. The composition disc can be adapted for use with a variety of temperatures and flow rates. The composition disc is renewable. Mating surfaces use a rubber O-ring or washer. The needle disc is used for micro-throttling service. Globe valve materials. Globe valves are designed to be used in a variety of process conditions. The specific condition dictates the type of material the valve will be made of. For example, the stainless steel globe valve is used in corrosive, high and low temperature services. The specialty alloy globe valve is used in high temperature and high pressure services. Some common alloys used are nickel and iron or steel and titanium. The bronze globe valve is used in low pressure and low temperature systems. The brass globe valve is used in low pressure and low temperature. The cast iron globe valve is used in water lubrication and some low pressure steam systems. When compared to gate valves, globe valves as shown in picture have a much greater pressure drop across the valve. Globe valves are designed to be installed in high-use areas. If a globe valve is installed in a low-use area, it tends to plug up even though it has a self-cleaning type design. Because of the 90 degrees turns in a globe valve, it cannot be unplugged with a straight rod device. Ball valves. Ball valves take their name from the ball-shaped, movable element in the center of the valve as shown in picture. Unlike the gate and globe valves, a ball valve does not lift the flow control device out of the process stream. Instead, the hollow ball rotates into the open or closed position. Ball valves provide very little restriction to flow and can be fully opened with a quarter turn on the valve handle. In the closed position, the port is turned away from the process flow. In the open position, the port lines up perfectly with the inner diameter of the pipe. Ball valves come in a variety of shapes and sizes as shown in picture. Larger valves require hand wheels and gearboxes to be opened but only require 1/4 turn on a handle. Ball valves should not be used for throttling service. During prolonged exposure, the ball seats and ball can be damaged, stopping the valve from sealing properly. Typically, ball valves are not designed for excessive temperatures. The seats are made of a plastic-coated material that tends to break down under high temperatures. Process technicians should be familiar with the temperature specifications of the valves. Ball valves do not generally seal as well as globe valves in high-pressure service. Some ball valves like multi-port valves are designed with multiple ports, so an operator can switch fluid sources without stopping flow. Check valves. A check valve is designed to prevent reverse flow and to avoid possible contamination or damage to equipment. The check valve limits backflow but is not considered a tight shutoff. Check valves come in a variety of designs and applications. Check valves have flow direction stamping on the valve body. A typical check valve design is the swing check, which has a hinged disc that slams shut when flow reverses as shown in picture. Flow lifts the disc and keeps it lifted until flow stops or reverses. The body of the check valve has a cap for easy access to the flow control element. Another design is the lift check, which has a disc that rests on the seat when flow is idle and lifts when flow is active as shown in picture. Special guides keep the disc in place. Like the swing check, it is designed to close when flow reverses. Lift checks are ideal for systems in which flow rates fluctuate. The lift check is more durable than the swing check. In the horizontal or vertical lift check design, a piston or ball is lifted up and out of the seat by process flow. A third design is the ball check design, which has a ball-shaped disc that rests on a beveled, round seat as shown in picture. The ball is down when flow is idle and up when flow is active. Special guides keep the ball disc in place. Like the swing check, it is designed to close when flow reverses. Ball checks are ideal for systems in which flow rates fluctuate or the fluid contains some solids. The ball check is as durable as a lift check and more durable than a swing check. A fourth design is the stop check design, which has characteristics of a lift check and a globe valve as shown in picture. In the closed position, the stop check disc is firmly seated. In the open position, the stem rises out of the body of the flow control element and acts as a guide for the disc. In the open position, the stop check functions like a lift check with one exception. The degree of lift can be controlled. Check valves operate by gravity and must be installed correctly. Ball, lift, swing, and stop checks come in horizontal and vertical designs. Check valves are designed to be used in a variety of process conditions. The specific condition dictates the type of material the valve will be made of. For example, the stainless steel check valve is used on corrosive, high and low temperature services. The specialty alloy check valve is used in high temperature and high pressure services. Some common alloys used are nickel and iron or steel and titanium. The bronze check valve is used in low pressure and low temperature as shown in picture. The brass check valve is used in low pressure and low temperature. The cast iron check valve is used in water lubrication and some low pressure steam services. Butterfly valves. Butterfly valves are commonly used for throttling and on-off service. The body of this type of valve is relatively small when compared with other valves and, therefore, occupies much less space in a pipeline. The flow control element resembles a disc. A metal shaft extends through the center of the disc and allows it to rotate 1/4 turn as shown in picture. A 1/4 turn is all it takes to fully open or close the valve. Technicians should be aware that butterfly valves are 100% open shortly after the valve handle passes 1/8 of a turn. During a throttling operation, a butterfly valve handle should be carefully secured. As flow enters the body of the valve, it contacts the disc and will cause it to open if the handle is not latched into position. Butterfly valves are used for throttling, however, it should be noted that they have non-uniform flow characteristics. 50% open may provide near maximum flow. Butterfly valves are designed to be operated at low temperature and low pressure. They are commonly found in cooling water and heat exchanger systems throughout the process industry. The seats in a butterfly valve can be made of natural gum rubber or suitable plastics. Plug valves. Quick opening, 1/4 turn plug valves are very popular in the process industry. The plug valve takes its name from the plug-shaped flow control element it uses to regulate flow as shown in picture. Plug valves provide very little restriction to flow and can be opened 100% with a 1/4 turn on the valve handle. In the closed position, the port is turned away from the process flow. In the open position, the port lines up with the inner diameter of the pipe. Plug valve design. Plug valves come in a variety of shapes and sizes. The plug valve is designed for fuel gas piping systems, low-pressure situations, slurry and lubrication service, on-off service, low-temperature service, and multiport operation. In on-off service, prolonged exposure can damage the seats. In low-temperature service, the seats are made of a plastic-coated material that tends to break down during higher temperatures. Plug valves maintenance. With proper care and maintenance, a plug valve can last indefinitely. Lubrication plays a big part in the life of a plug valve. Plug valves depend on a lubricant inside the body of the valve. This lubricant helps the valve provide a leak-free seal. A plug valve should never be used for throttling. Excessive wear will result if a plug valve is throttled, and the valve's ability to obtain a positive seal will be jeopardized. Most plug valves should be limited to temperatures under 480 degrees Fahrenheit or 248.9 degrees Celsius. Higher temperatures displace the grease and cause the plug and valve body to seize or warp. Diaphragm valves. In a chemical plant, a variety of slurries, corrosive or sticky substances are transferred from place to place. Standard valves would have a difficult time with this type of product, but diaphragm valves are specifically designed for the job. Diaphragm valves use a flexible membrane and seat to regulate flow. The handwheel operates just like the handwheel on a gate or globe valve. The stem is attached to a device called the compressor. The compressor pushes on a flexible diaphragm. The internal parts of the valve never come into contact with the process material. The diaphragm conforms to the setting on the handwheel. Diaphragm valves typically are used in low-pressure applications. The diaphragm valve seats are made of chemical-resistant plastic, rubber, or neoprene. This type of valve does not use packing. Diaphragm valves come in two designs, weir and non-weir. The weir diaphragm valve has a weir or a dam located in the body of the valve as shown in picture. Fluid must go over the top of the weir and under the diaphragm in order to exit. There is a large pressure drop across the body of the valve. It uses thick, durable diaphragm materials. The non-weir, or straight-through diaphragm valve, has a flexible membrane that extends across the pipe as shown in picture. Pressure drop across the valve depends on the position of the diaphragm. Diaphragm valves as shown in picture can handle corrosive fluids and fluids that are ultra-pure such as demineralized boiler feed water. They must be used in low-pressure applications and in operations that have moderate temperature and pressure fluctuations. Relief and safety valves. Relief valves. Relief valves have been engineered to respond automatically to sudden increases of pressure in liquid surfaces. A relief valve is designed to open at a predetermined pressure. In a relief valve, a disc is held in place by a spring that does not open until the system pressure exceeds operating limits as shown in picture. Tremendous pressures can be generated in process units. Relief valves are designed for pressurized liquid service. They do not respond well in gas service. Relief valves are designed to open slowly. This is a poor feature for gas service. Another reason relief valves are not used in gas service is because of the damage high-velocity gas would do to the seats and disc. Steam cut and wire drawn are two terms applied to damaged trim. Relief valves vary in design and style. Relief valves have a specific amount of travel, or lift, which varies from fractions of an inch to several inches. When a relief valve is lifted until it completely compresses the spring, it is said to be in the fully open position. The difference between the initial liftoff pressure and the pressure of the fully open position is called accumulation. A relief valve consists of the following components: a cap that protects the adjusting screw, the lock nut, and the internal components of the relief valve, an adjusting screw and lock nut, a casing or body, a spring and spring washer that hold a constant tension against the disc, inlet and outlet ports, a disc or plug, a spindle or stem that is threaded and screwed into the flow control element to guide vertical movement of the disc, and a seat. When a relief valve opens, it is relatively easy to detect flow through it. Cold service relief valves ice up around both the inlet and discharge ports of the valve. Warm service valves are hot on both sides of the valve. Most relief valves discharge to the cold or warm flare drum and ultimately to the flare. Some relief valves, such as those in steam service, discharge to the atmosphere. Some relief valves have a handle on the side to check the function of the valve. This is a maintenance function, however, and the technician should not use this lever. The two advantages of relief valves are that they will reseat as soon as the pressure drops below the relief pressure and the spring tension is adjustable. Safety valves. Safety valves are considered to be a process system's last line of defense. They are designed to respond quickly to excess vapor or gas pressures. When a system overpressures, safety valves respond to allow excess pressure to be vented to the flare header or to the atmosphere. This venting prevents damage to equipment and personnel. This type of valve is very similar in design to a relief valve. The three major differences between a relief and a safety valve are liquid versus gas service, the pressure response time, and a larger exhaust port. Relief valves are designed to lift slowly, whereas safety valves tend to pop off. Because the exhaust port is much larger in a safety valve, it can release more flow at much lower velocities. This feature keeps the trim from being damaged. Safety valves are classified by how they open and the number of adjusting rings used. Some safety valves reseat after lifting, others do not. Valves that do not reseat must be taken to the shop and mechanically reset. A safety valve consists of the following components as shown in picture: a cap that protects the adjusting screw, the lock nut, and the internal components of the safety valve, a spring adjusting screw and lock nut, a casing or body, a spring and two spring washers that hold a constant tension against the disc, an inlet and a large outlet, a disc or feather and disc guide, a spindle or stem that is threaded and screwed into the flow control element to guide vertical movement of the disc, a seat, and huddling chamber, an adjusting ring and ring pin, lifting levers, and pivot pins. Automatic valves. The chemical processing industry uses a complex network of automated instrument systems to control its processes. The smallest unit in this network is called a control loop. Control loops usually have a sensing device, a transmitter, a controller, a transducer, and an automatic valve as shown in picture. Because automatic valves can be controlled from remote locations, they are invaluable in processing. The most common type of automated valve is a globe valve because of its versatile on-off or throttling capability. Control loops use on-off or throttling type valves to regulate the flow of fluid into and out of a system. Automatic valves can be used to control pressure, temperature, flow, or level. Automatic valves are categorized as either control valves or spring or weight-operated valves. Control valves can be air-operated, electrically operated, or hydraulically operated. Spring or weight-operated valves hold the flow control element in place until pressure from under the disc grows strong enough to lift the element from the seat. A check valve would fall into this category. Any of the valves in this chapter can be automated by the installation of a device known as an actuator. The actuator controls the position of the flow control element by moving and controlling the position of the valve stem. Actuators come in three basic designs: pneumatically or air-operated, electrically operated, and hydraulically operated. Pneumatic actuators. Pneumatically operated actuators are the most common type. They come in three designs: diaphragm, piston, and vane. Each design converts air pressure to mechanical energy. The diaphragm actuator is a dome-shaped device that has a flexible diaphragm running through the center as shown in picture. It typically is mounted on the top of the valve. The center of the diaphragm in the dome is attached to the stem. The valve position, on or off, is held in place by a powerful spring. When air enters the dome on one side of the flexible diaphragm, it opens, closes, or throttles the valve, depending on the design. The piston actuator uses an airtight cylinder and piston to move or position the stem. It is commonly used with automated gate valves or slide valves. It is used where a lot of stem travel is needed. Vane actuators direct air against paddles or vanes and are frequently used on quarter-turn valves. Common terms for pneumatic actuators include air to open, spring to close, The valve fails in the closed position if the air system goes down. The air line typically is located on the bottom of the dome. Air to close, spring to open. The valve fails in the open position if the air system goes down. The air line is typically located on the top of the dome. Double acting, no spring. Air lines are located on both sides of the dome. Electric actuators. Electrically operated actuators convert electricity to mechanical energy. Examples are the solenoid valve and the motor-driven actuator. Solenoid valves are designed for on-off service. The internal structure of a solenoid resembles that of a globe valve as shown in picture. The disc rests in the seat, stopping flow. The stem is attached to a metal core or armature that is held in place by a spring. A wire coil surrounds the upper spring and stem. When the wire coil is energized, a magnetic field is set up, causing the armature to lift and compress the spring. The armature is held in place until the current stops. A motor-driven actuator is attached to the stem of a valve by a set of gears. Gear movement controls the position of the stem. Mechanical devices limit the movement of the stem by stopping the motor when open and when closed. Hydraulic actuators. Hydraulically operated actuators are very strong. They convert liquid pressure to mechanical energy. The hydraulic actuator uses a liquid-tight cylinder and piston to move or position the stem. It is commonly found in use with automated gate valves or slide valves. It is used where a lot of stem travel is needed. Valve symbols. Each type of valve can be represented by a symbol. Valve symbols are shown in picture. A valve is a device used to control, stop, start, or restrict or direct the flow of fluids. Process technicians classify valves by flow control element, the part of the valve that regulates or controls function and operating conditions such as pressure, flow, or temperature. A gate valve places a movable metal gate in the path of a process flow in a pipeline. Gate valves are considered excellent devices for process services that are used infrequently. A globe valve places a movable metal disc in the path of a process flow. This type of valve is the most common one used for throttling service. Ball valves and plug valves have a hollow baler plug-shaped movable element in the center of the valve that rotates into the open or closed position. These valves provide very little restriction to flow. They should not be used for throttling service or in high temperature or high pressure service. Check valves are used to control flow direction and to prevent contamination of or damage to equipment. A butterfly valve has a pivoting flow control element shaped like a flat disc. Diaphragm valves use a flexible membrane to throttle sticky, viscous, or corrosive materials. Relief valves automatically respond to sudden increases in pressure in liquid services. Safety valves do the same thing in gas services. The three major differences between a relief valve and a safety valve are liquid versus gas service, the pressure response time, and the larger exhaust port of the safety valve. Relief valves are designed to lift slowly, whereas safety valves tend to pop off. Actuators are devices in a control loop that automatically adjust the position of the valve stem on a control valve. Maintaining equipment is an important part of an operator's job. On gate valves, stem threads exposed to weather need to be lubricated. The packing should be inspected, and the gland nuts tightened evenly if a leak is found. Valve stems should not be painted, and every effort should be made to keep them free of dirt and dust. Process technicians should not over-tighten a gate valve to avoid damaging the seats. When the gate is on the bottom, a wrench should never be used to wedge it closed. That's all, gentlemen. I hope this training course have refreshed your knowledge regarding the valves and their applications. Good day and good luck.